This building looks ordinary. A facade, some windows, a door people walk through without a second thought. But before we explore how it actually works, consider this. Buildings consume a staggering share of the world's energy, far more than most people ever realize. Behind every wall, above every ceiling, beneath every floor, there is a hidden system quietly doing the work of keeping people comfortable. Most of it goes completely unnoticed. Today, we're going to change that. We're going to pull back the surface, layer by layer, and reveal the engineering that makes a modern building possible, one hidden system at a time. Energy doesn't disappear from a building all at once. It leaks, slowly, quietly, continuously, through the places we least expect. The roof radiates warmth into the night sky. Walls conduct heat outward in winter and inward in summer. Windows, for all their beauty, are often the weakest link in the entire structure. And then there are the air leaks, tiny gaps around doors, outlets, and seams, letting conditioned air escape and unconditioned air sneak in. Individually, each leak seems insignificant. Together, they represent the single largest source of wasted energy in most buildings. Finding them is the first step toward stopping them. To understand why any of this matters, we have to go back to a single, unbreakable law of physics. Heat always moves from warm to cold. It doesn't pause. It doesn't negotiate. In winter, heat inside a warm building constantly pushes to escape into the cold outdoors. In summer, the reverse happens. Heat from the hot exterior pushes its way in. This relentless movement is the force every building system is ultimately designed to manage. Insulation, glazing, ventilation, heating, cooling, none of it exists in isolation. All of it exists because of this one simple, immovable fact about how heat behaves. The first line of defense against that constant heat flow is something most people never see. Insulation. Packed inside the walls, the roof, and sometimes the floor, high-performance insulation material works by slowing the rate at which heat can pass through. It doesn't stop heat flow entirely, as nothing can, but it dramatically reduces how fast that flow happens. The better the insulation, the harder a building has to work to lose its warmth in winter or gain unwanted heat in summer. It's simple in concept, but its impact on a building's total energy use is enormous, making it one of the most important hidden systems of all. Insulation alone isn't enough. Even the best insulated wall can be undermined by something as small as an unsealed gap around a window frame or an electrical outlet. That's where the airtight building envelope comes in. A continuous, sealed barrier wrapped around the entire structure, engineered to eliminate uncontrolled air leakage. Every seam, every joint, every penetration is carefully sealed. The result is a building that holds onto its conditioned air instead of losing it to drafts and gaps. Without this airtightness, even the most advanced insulation would be working against a constant stream of air slipping past it. Of all the components in a building's envelope, windows have always been the hardest to get right. We want the light they bring in, but not the heat that comes with it. High-performance windows solve that problem through low-emissivity triple glazing. 3 layers of glass separated by insulating gas, coated with a microscopic layer that reflects infrared heat while still allowing visible light to pass through. The effect is striking. Rooms stay bright and connected to the outdoors, while the heat transfer that once made windows a liability is dramatically reduced. It's one of the clearest examples of engineering quietly solving a problem most people never even think about. Even the best windows can't stop every bit of solar heat from a fundamentally different angle. Heat that arrives before it ever touches the glass. That's the role of exterior shading systems, placed strategically across a building's facade to intercept sunlight before it can heat the surface. By blocking solar gain at the source, these systems reduce the load placed on everything downstream. The cooling equipment, the ventilation, the entire thermal balance of the building. It's a simple principle with an outsized impact. It's always more efficient to stop unwanted heat before it enters a space than to remove it once it's already inside. Every building needs fresh air, people need oxygen, and stale air needs to leave. But simply pumping conditioned air outside and pulling unconditioned air inside would waste enormous amounts of energy, unless that energy can be recovered. Heat recovery ventilation does exactly that. As outgoing exhaust air passes near incoming fresh air, a core inside the system transfers warmth from one stream to the other without letting the air itself mix. The fresh air arriving in the building is preconditioned before it even enters a room. dramatically reducing the energy needed to bring it to a comfortable temperature. All of that conditioned air still needs somewhere to go, and that's the job of the air handling unit. Sitting at the heart of a building's mechanical system, it draws in air, processes it, and distributes it efficiently throughout every floor and every room. It's the quiet engine behind comfort. Rarely seen, rarely thought about, but constantly working to make sure conditioned air reaches exactly where it's needed, exactly when it's needed, without unnecessary waste along the way. Here is one of the most important shifts in modern building engineering, and one of the most misunderstood. A heat pump doesn't generate heat the way a furnace does. It moves heat. Using a refrigeration cycle, it extracts warmth from one place, even cold outdoor air, and delivers it to another. In summer, it works in reverse, extracting heat from inside the building and releasing it outdoors. Because moving heat takes far less energy than creating it from fuel, heat pumps achieve efficiencies that traditional heating systems simply cannot match, making them one of the cornerstones of an energy-efficient building. Once heat is delivered into a building, how it reaches each room matters just as much as how it was generated. Radiant heating and cooling moves comfort directly through surfaces. Tubing embedded in floors or ceilings carries warm or cool water, gently regulating room temperature without the drafts and uneven hotspots common to forced air systems. Because radiant systems heat and cool objects and surfaces directly, rather than just the air around them, they achieve consistent comfort while using meaningfully less energy than conventional air-based systems. Proof that how energy is delivered matters as much as how it's produced. Not every system in a building moves heat. Some simply waste less of it. Traditional lighting converts much of its energy into heat rather than light, energy that serves no purpose and often adds unwanted warmth to a space. LED lighting changes that equation entirely, producing the same brightness using a fraction of the electricity and releasing far less wasted heat. It's one of the simplest upgrades a building can make, and yet multiplied across thousands of fixtures running for thousands of hours, the cumulative impact on total energy use is significant. Efficient lighting still wastes energy if it's left running in a room nobody is using. That's the gap occupancy sensors are designed to close. Quietly mounted in ceilings and on walls, these sensors detect whether a space is actually occupied, automatically switching lighting on when someone enters and off when they leave. It's a small piece of engineering with an outsized effect, ensuring that even the most efficient lighting system isn't burning energy in empty hallways, vacant offices, or unused conference rooms. Each of the systems we've seen so far, insulation, ventilation, heating, lighting, was engineered to perform brilliantly on its own. But real efficiency comes from coordination, not isolation. The building automation system ties everything together, linking HVAC, lighting, and sensors into a single intelligent platform. It constantly adjusts, balancing comfort against energy use across the entire structure in real time. What were once independent systems, each solving its own piece of the puzzle, now operate as one coordinated whole. Each system informed by the others, each decision made with the full building in mind. None of this coordination would be possible without visibility, and that's exactly what smart energy monitoring provides. Smart meters track a building's energy consumption continuously, in real time, breaking down exactly where power is being used and when. That awareness transforms every other system connected to it. The building automation system can only optimize what it can actually measure. Without this layer of visibility, inefficiencies would remain hidden indefinitely. With it, even small shifts in behavior or equipment performance become immediately apparent, ready to be corrected. Up to this point, every system we've explored has focused on using less energy. Now the building begins generating its own. Rooftop solar panels convert sunlight directly into clean electricity, generated right where it will be used. There's no transmission loss from a distant power plant, no reliance on the broader grid for every watt consumed. The building, once purely a consumer of energy, starts to become a producer, a shift that changes its entire relationship with the energy system around it. Solar power has one obvious limitation. It's only generated when the sun is shining, but it isn't always needed at that exact moment. Battery energy storage solves that mismatch, capturing electricity as solar panels produce it and holding it in reserve for use later, in the evening, overnight, or during periods of high demand. What would otherwise be a fixed, inflexible source of power becomes something far more useful. Energy available exactly when the building needs it, not just when the sun happens to provide it. Electricity isn't the only thing worth storing. Thermal energy storage applies the same principle to heating and cooling. Building up chilled water or thermal mass in advance, then drawing on it later to meet cooling demand, without running equipment at full power during the building's peak hours. Just as a battery shifts electricity across time, thermal storage shifts cooling load across time, easing strain on equipment and reducing the building's draw on the grid exactly when that grid is under the most pressure. With generation and storage in place, the building's relationship with the wider electrical grid fundamentally changes. A smart grid connection enables genuine two-way interaction. The building can draw power when it needs it, and send power back when it has more than it needs. It's no longer a passive consumer sitting at the end of a power line. It becomes an active participant in a larger, interconnected energy network, contributing as much as it draws, depending on the moment. That same energy intelligence now extends beyond the building's own walls and into the vehicles that visit it. EV charging infrastructure turns parking spaces into charging hubs, allowing buildings to fuel electric mobility directly from the energy systems already humming within them. A building that generates its own power, stores it, and manages it intelligently is uniquely positioned to support the next generation of transportation, extending its reach from the rooms inside to the vehicles parked just outside. True efficiency isn't limited to energy alone. It extends to water as well. Rainwater harvesting captures precipitation before it ever reaches a storm drain, while gray water recycling reuses water from sinks and showers for purposes like irrigation or flushing. Together, these systems reduce a building's reliance on potable water supplies, applying the same underlying philosophy as everything we've seen so far. Capture what would otherwise be lost and put it to productive use instead of letting it go to waste. No single system we've explored achieves net zero on its own. Insulation alone isn't enough. Solar alone isn't enough. Storage alone isn't enough. It's only when every system works together, envelope, ventilation, heating, lighting, generation, and storage, all coordinated as one, that a building can produce as much energy as it consumes over the course of a year. Net zero isn't a single piece of technology. It's the integration of dozens of hidden systems, each one we've revealed working in concert toward a single outcome. Even a fully integrated net zero building benefits from ongoing intelligence, and that's where the AI digital twin comes in. Running continuously alongside the physical structure, it analyzes occupancy patterns, weather forecasts, and real-time energy data, constantly fine-tuning how every system performs. It's not a one-time achievement, but an ongoing process. A digital counterpart to the building that learns from it, adapts to it, and helps it perform better with every passing day. Pull back far enough, and what emerges is not a collection of separate technologies, but a single ecosystem. Batteries, hydrogen storage, thermal storage, and the grid all working together, each compensating for the limitations of the others, each strengthening the overall system. What started as isolated solutions to isolated problems has become something far more powerful. An integrated energy building, where every hidden system we've revealed contributes to one unified, intelligent whole. And so the story that began with a single, ordinary-looking building expands outward into something much larger. Multiply this building by thousands, connect them through shared grids and shared intelligence, and what emerges is an interconnected, sustainable city. One where buildings are no longer passive structures consuming resources, but active energy assets contributing to the system around them. Every hidden system we've uncovered, from insulation to AI, points toward this same future. A built environment that doesn't just use energy but understands it, manages it, and shares it.